In traditional job shop, a part might travel back and forth across the facility 5 or 6 times before it's finished. Each trip adds time, handling costs, and risk of damage. In a cellular manufacturing layout, the same part stays in one cell from start to finish. The difference isn't just aesthetic, it's measurable in lead time, inventory, and cost. This week, we cover the tools that let you design the cellular structure from scratch, how to plan departments, how to use direct clustering algorithm, and rank order clustering algorithm to form manufacturing cells from a machine part matrix, and how to measure and visualize the flow between departments quantitatively and qualitatively. So, planning departments, group workstations that perform similar functions, similar products, components, or processes. The type of department you create depends entirely on the product characteristics. Product layout, fixed materials location, product family, GT layout, process layout, which is also job shop. The spectrum runs from the flow shop on the left, high volume, low variety, to job shop on the right, low volume, high variety. The volume variety chart from week 7 tells you exactly where on the spectrum your product mix sits. Product family or group technology departments aggregate medium volume variety parts into family based on similar manufacturing operations or design attributes. The machines required to produce that family are then grouped together to form a cell. The most common cell design groups machines, employees, materials, toolings, and material handling equipment together. Everything the part family needs in one physical space. The before and after comparisons is striking. Before group technology, parts travel across the facility in all directions. What engineers call spaghetti flow, turning is in one area, milling in another, heat treatment somewhere else. Every part crisscrosses the floor. After group technology, 3 cells, each self-contained. Raw materials go in, finished parts come out. Flow is linear, predictable, and controllable. Cell formation approaches range from simple manual methods, classification and coding production flow analysis, to computational techniques like DCA and ROCA, which we will cover now. The full benefits of cellular manufacturing are achieved when cells are designed, controlled, and operated using 3 principles: just in time, total quality management, and total employee involvement. Together, they can produce 3 categories of outcomes: reduction, simplification, and improvement. Every one of these reduction and improvement feeds directly into facility design decisions. Fewer machines needed, smaller building footprints, less storage equipment. The cell is not just an operational concept, it's a facility planning tool. So, the direct clustering algorithm forms manufacturing cells from a machine part matrix, A binary, where A1 means that part requires processing by that machine. Here's a practical tip. Steps 2 and 3 are easy to automate in Excel. If you're working by hand, take it one row or column at a time and be systematic about checking every entry. We have 6 parts and 5 machines. For example, part 1 requires machines 1 and 3, as you can see here. Part 3 requires machines 3 and 4 and 5, 3 ones. The full row counts are part 1, 2, part 2, which is part 1, and part 3, 4, 5, and 6, as you see. So, step 1, order rows in descending total. Part 3 goes first with 3, then part 6, 4, 1, tied at 2 each. Then parts 5 and 2 with 1 row order. For columns, ascending orders of ones. The reordered matrix is on screen, as you see. Notice, notice already some clustering is visible. Ones are starting to group toward the upper left and lower right, but we're not done yet. As you can see in step 2, column sorting, we look at row 1, which has ones in M5 and M4, both already on the left column. Column M2 has 1 in part five's row, We shift it left based on that. Only one column shift is needed in this example. In the final step, we form the cells. The upper left block contains machines M2, M4, M5, and parts 3, 5, 6. That's cell 1. The lower right block contains machines M1 and parts 1, 2, and 4. That's cell 2. Every part's processing requirements are entirely within one cell. No intercellular travel needed in this example. Example 2 here shows what happens when a clean cell separation is impossible. After ordering machine 2 is needed by parts in both candidate cells. It can't belong just to one. That's the conflict. Three alternative cells formations are possible. There's option A, option B, and option C, which all compromise of different cells that we can use. Five resolution strategies are available. First, place the bottleneck machine at the boundary between cells or make it adjacent to both. Second, redesign the part so it's no longer crosses cells. Third, outsource the conflicting part. Fourth, duplicate the machine so each cell has its own. Fifth, if demand is high enough, providing a second machine of the conflicting type is often the most practical solution. It eliminates intercellular travel permanently. The rank ordering cluster algorithm reaches the same result as the other one, but uses a different mechanism. Instead of simply counting ones, the rank order clustering algorithm assigns binary weights to each position, treating a 1 in an early column as more significant than a 1 in a late column. Using the same 6 by 5 matrix, columns are assigned weights from right to left. For each part row, we sum the weights of the columns that contain a 1. Part 1 has 1 in M1 and M3. And in part 2 has only 1 in M1. Part 3 has 3 ones in M3, M4, and M5. So, after re-ranking rows, we apply the same binary weight logic to columns, this time from bottom to top. For the rows column, 1 gets the highest decimal equivalent because parts 1 and 4 both have 1s. There. And those parts rank near the top. The column order that emerges puts machine 1 first, then third machine, then second machine, then fourth, then fifth. Very similar to what we've seen before. After one or two iterations, the matrix stabilizes with the same two cell blocks as before. The two algorithms converge to the same answer on most problems. Once departments and cells are defined, we need to decide how to arrange them within the facility. The basis for that arrangement is flow between departments. Flow measurement takes two forms, quantitative and qualitative. Most real facilities need both. A manufacturing floor with a cafeteria, an office, and receiving dock has material flow, relationships, and organizational ones. Use both tools and weight, and then use them appropriately. So, let's close this down. Next week, we move into space requirements, translating these departments' arrangements into actual square footage. Thank you for listening and have a good day.